Okay, Chem, this is an example of what we call a molar heats problem. So the problem reads, the change in enthalpy for the reaction of propane burning is negative 2043 kilojoules. If I want to generate enough heat to cook an entire steak, which requires 255,000 kilojoules, how many grams of propane do I need? So there's actually a lot of hidden information in this particular question. So the first thing we need is a balanced chemical equation. So propane, which we use in a lot of our gas grills, burning, let's weed out the clues that we have. Burning means it's chemically combined with oxygen. And when you combust a hydrocarbon, the products are always carbon dioxide and water. It also tells us this number here says negative 2043 kilojoules. There's no such thing as negative heat. The negative sign indicates direction of flow. So the system and the surroundings are the only two parts of the universe we're concerned with. In this case, the system is the burning of the propane, and negative means that energy is leaving this system, meaning energy is a product. So 2043 kilojoules of energy is released or given off. That negative sign means it's leaving the system. So that being said, my actual given in this particular case is 255,000 kilojoules of energy. Now, what this equation means is when I burn propane, how much energy do I want to release? So because propane is the topic of conversation, we're going to want a coefficient of 1 by propane. In thermochemical equations, if you are balancing the equation, then you would want to have a 1 by the subject of the problem in this case. So I'm going to balance it first. That's the key. So when 1 mole of propane burns, it will require 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. So these are all conversion factors that we can get from this particular problem, depending on the conversion factor that we need. I can make a total of 8 conversion factors from this. I don't need all 8 conversion factors, though, so I'll make a couple as examples. But we don't need but one of them. So here's a couple examples. You can also flip these. For example, if 1 mole of propane gives off 2043 kilojoules, I can make 2 different conversion factors from that equivalency statement. And which one I will use depends on the problem. I need kilojoules to cancel out, so I'll need the kilojoules on the bottom, and then I'm trying to get to moles of propane because I know to get to moles, the next step would be grams. So we all know how to change moles to grams by multiplying by the molar mass. So there's 3 carbons, and add that to 8 hydrogens. And I go to molar mass of 44.094 grams. I multiply across the top and divide by the bottom, and I get an answer of, in my calculator, of 5503, and then a bunch more numbers that I'm not going to need, kilojoules. I'm going to round to 3 sig figs. You notice I can't answer in 3 sig figs. If I do that, that's only 2. So I need scientific notation. There's my answer. Next problem. When a 1.82 gram sample of ethanol combusts surrounded by 220 grams of water in a calorimeter, then temperature rises from 22.0 degrees Celsius to 75.0 degrees Celsius. Calculate the enthalpy of the reaction that took place in kilojoules. So this is a calorimeter problem. So first year you might have done calorimetry with what's called a coffee cup calorimeter, like such, where you would put 2 chemicals in there and measure the change. Coffee cup, because coffee cups are always insulators. This, however, is not exactly the same thing because it tells us it's combusted. I want to think of a bomb calorimeter. So how a bomb calorimeter works is I have a box inside of a box. And inside this box here is where my combustion is going to happen. So I'm going to take CH3CH2OH, and when I say combust, I mean add oxygen to it. And I'm still going to produce carbon dioxide and water. Combustion of a hydrocarbon always produces these happy substances. So now I'm going to balance. And believe it or not, leaving a 1 here will actually make things a little bit easier. Now in this case, it doesn't matter. 7, so there we go. Now I'm balanced. How these problems work is that the energy lost by this chemical reaction, because this is going to be exothermic, all combustion reactions are exothermic, plus we know that heat was released to the water. So in this case, you have the combustion reaction happening here, and the heat is leaving the system, which is the combustion reaction, and entering the surroundings, which is the water. So the heat that leaves the combustion reaction is equal to the heat that enters the water. So this guy's going to lose and this guy's going to gain. They're going to be equal and opposite. So you can do MCAT for the propane combusting, and you can do MCAT we'll call this the combustion reaction, and you can do MCAT for the water. So what we're looking for is the amount of heat. So we don't need to necessarily know anything more about the propane. We can say that the heat lost by the propane is equal and opposite of the heat gained by the water. So in this case, Q is going to be the mass of water, 220. The specific heat of water, which is well known. And then the change in temperature of water. The change in temperature is 75 minus 22. Again, it's easier for combustion reactions. It's easier for thermochemistry in general, is if we deal with positives, recognizing that negatives only tell us direction of flow. So 53 degrees Celsius is my temperature change. So the heat in this case in joules is going to be 48,785 joules. I'm going to round to 3 sig figs, answer in kilojoules, and I will get 48.8 kilojoules is what is released. So you can either put a negative sign or you can say released. They mean the same thing.